Welcome to third and final session of this lecture, interfacing of memory and I/O devices with 80. There I covered different type of memory, especially RAM on ROM, how to interface with the 8085 processor. To talk about the interfacing, basically it is a concept that refers to a point of interaction between components, and it's applicable at the level of both hardware and software. Interfacing circuit and programming is required for the microprocessor to connect different types of hardware modules like input devices, output devices, memory elements, which will be used for different programming purpose. It is known that memory device internally, uh, microprocessor 8085 don't have memory. So to store the required program and data, we need to connect the memory externally. At the same time, to provide the different types of coding and data, we require input device as well. And after the execution of the program, to observe the changes of different data or basically the result from the programming, we need some output device as well. So it is very important to understand how we can connect the input and output devices with the microprocessor 8085 and how to write its required program. This allows a concept how to connect different components such as graphics card, internet browser, and many more devices to function independently while using interface to communicate with other component via input output system and associated protocols. Come back to the 8085 processor. It is well known that 8085 is having three type of buses, namely address bus, data bus, and control bus. Address bus is used to identify the memory element or memory device, input device, output device, whereas data lines are used to transfer the information between the processor and outside devices, whereas control line function is to specify type of operation processor want to perform, such as whether processor want to perform read operation, write operation, or whether processor want to interact with the memory devices or input output devices. That is basically the function of control lines. Here are the different types of input output lines and control lines present with the 8085 processor. It has 16 number of address lines, 87 to 80, which is known as the lower order address, and multiplex data bus. That means these lines for the first cycle act as address lines to carry the lower order address, and for the next cycle of the same process it used to carry the information. That's why it is function as a data bus. Whereas the higher order address lines A8 to A15, a single function it performs, that it only carries the info address, higher order address from the which is generated by the processor itself. The control lines are available in the form of AEIE, that is address latch enable, whose function is to demultiplex the address lines from the AD0 to AD7. IO inverse signal, whose function is to differentiate whether processor want to perform the IO operation or memory operation. As the signal indicates, during the input-output operation, the signal is high or at logic 1, whereas in case of memory interfacing, the signal becomes low to indicate that processor want to perform the memory related operation. Read signal basically informs the device processor want to read from the device, that means kind of input action, whereas write signal indicates device processor want to write some signal to the device, that means count kind of output action. So these are the control signals, address lines and data lines used to interact with the input output device and memory element. Now generation of control signals, earlier we was discussing about memory read and memory write cycle which used for the memory interfacing. This time I shall discuss about how to generate the input read signal and out input write signal. IO read signal and IO write signal. As I said, during the IO operation, IO signal becomes 1. So similar to the memory read and memory write combination, here it combines, that means IO inverse signal combines with the RD signal and WR signal in this fashion to generate a active low IO read signal when read bar goes low, whereas it generates a active low IO write signal when WR becomes 0. So during the write operation, IO write signal becomes low, and during read operation, IO read signal becomes low. These two signal will be required for our discussion to interface with the input output devices. Now directly go to the interfacing technique of input output devices. Using IO devices, data can be transferred between the microprocessor and outside world. This can be done in a group of 8-bit using the entire data bus. This is called parallel IO. As I discussed, the processor is having 8-bit data lines. So processor can transfer all 8-bit data to or from the processor with the IO devices, and if it does so, this is called parallel IO interfacing. Whereas apart from the data lines D0 to D7, processor is having two serial input output lines as well, namely serial input data and serial output data lines. With the help of these two lines, processor can send or receive 1-bit information at a time, and this is known as serial communication. Now, type of parallel interface. That means when processor or what are the different way to interface with the IO device in parallel interfacing mode. It can be performed in two ways, that is called memory mapped IO and IO mapped IO. What's the concept of memory mapped IO? It considers them like any other memory location. So in case of memory mapped IO, they are assigned 16-bit address. Basically, all the 16-bit address lines of the processor connected to the input output element, thus it considered as a memory location. The exchange of data with these devices follows the transfer of data with the memory. The user uses the same instruction used for the memory interfacing or memory access, like LDA, STA, move. This type of instruction here also used for communication with the input output devices. Other two instruction specially dedicated for the input output interfacing belongs to the group IO mapped IO. In IO mapped IO, the port number is specified within the instruction in or out. It is basically 8-bit address of the device, not like 16-bit memory. It is a 8-bit address placed onto the address lines, mainly lower order address lines, but later I will discuss. It is that same address is also available in higher order address lines as well. As it is 8-bit address, so obviously its range is 002 FF. That means 256. 002 FF means total 256 number of combinations are there. So 256 number of IO device can communicate. 256 number of input or 256 number of output device can communicate with the processor. Each instruction format is in followed by the 8-bit address of the device. For example, in 08, where 08 is the address of the device data, and if we write so, then data will transfer to accumulator from the input device. Here we must remember that if we are using in instruction followed by the address, data will always read from the microprocessor from the input device and kept in the accumulator only, not in any other register like B, C, D, E or HL. Not in any other register. It is not possible. So after read operation from the input device, data is always available in the accumulator only. Similarly, out instruction followed by the 8-bit output address. For example, out 01, where 01 is the address of the output device. In this case, data will transfer from the accumulator to the output device. Like in instruction, here also the data from the accumulator will transfer to the output device, not any other register. Now, if we draw a difference between the IO mapped IO and memory mapped IO, we can point few things. First of all, as I discussed that IO is treated as a memory. So all the 16-bit address lines are used as because the particular IO device treated as the memory. So user have to use all the 16 address lines to interface with the input output devices. Whereas in case of IO mapped IO, only the 8-bit address are to be used. So if we do so, total 2 to the power of 16 combination will generate. So 64K location will be dedicated for that. Thus, 64,000 number of input output device can connect with the device. Although practically it is not possible, theoretically we can say maximum number of input output device will be 64,000. But if all the addresses are dedicated for the input output device, we cannot connect any memory, and without memory element, writing program for the 8085 processor will not be possible. So practically it is absolutely not possible, but theoretically we can say these many number of input device or output device can connect with the system. Whereas in case of IO mapped IO can address 2 to the power of 8, that is 256 locations or combinations will be generated. Thus 256 number of input device and 256 number of output device can connect with the processor. So as if we connect 16 number of address lines, so more number of decoder hardware will be required. We need to combine all the 16 lines, and by decoding them we need to produce a specific control signal for the input device or output device. So obviously hardware will be little bit complicated. In case of 8-bit address, less number of lines are to be decoded, so hardware will be less complicated. So this point is discussed. If we dedicate few segment of the memory location or few number of memory location for the IO device, so amount of memory is available for the 8085, that will reduce, because those address lines which are dedicated for the input output devices, that cannot be used as a memory, so less number of memory will be available. Whereas in case of IO mapped IO, as no memory location are used for the input output device, that's why whole memory address space is available. That means 256 for the at IO and total 64,000 memory location will be available for the processor to write the program or to store the data. Next, memory. In case of memory mapped IO, as I said that we need to use the LDA, STA or move instruction for the communication with the input output device. So memory instruction are used, but for the IO mapped IO, specially two instructions are available here. One is in, other is the out. Memory control signals are used. Here MEMR, MEMW, these kind of control signals are used to generate the control enable signal for the input output device, whereas in case of IO mapped IO, IO read or IO write signal are used for accessing input output device. Here, as the input output device is considered as the memory element, so some arithmetic or logical operation can also be performed directly, whereas in this case IO mapped IO, arithmetic and logical operation cannot be performed. And if we go for the memory mapped IO, then data can be transferred not only with the accumulator but also with any other registers available in the system. In case of IO mapped IO, data transfer only between the accumulator and the IO device is possible, but with no any other register. These are the differences we can draw between the memory mapped IO and IO mapped IO. First, let me discuss about the interfacing technique of output device. So we must remember that output devices are usually slow with respect to 8085 processor. So if any data sent by the processor, and due to this feature, microprocessor in output device cannot read the signal sent by the processor, or if it is lost, then we cannot recognize the output. That's why it is always recommended to use some latching device externally to save the information sent by the processor. Do remember, the output is usually expected to continue appearing on the output device for a long period of time, because we need to read or understand the output. It must be displayed for quite long time. So, but the information do not present on the data line for long time. That's why externally latching device must be connected. Given that data will be present on the data lines for a very short period of time, it has to be latched externally. To do this, the external latch should be enabled when the port address is present on the address bus, the IOM signal is set high and WR is set low. When processor is sending some information to the output device, that external latch has to be enabled and WR signal must be low to activate the system. The resulting signal would be active when the output device is being accessed by the microprocessor. Decoding the address bus follows the same technique discussed in interfacing memory. Now, about the input devices, the basic concepts are similar to interface with the output device. The address lines are decoded to generate a signal that is active when the particular port is being accessed. When we want to access the input device, that system must be activated, and activation is done by decoding the port address. An IO-RD signal is generated by combining the IO-M and RD signal as discussed earlier. So, not like output device, here a buffer will be sufficient. We no need to connect the latching device with the input system, but some buffer device, mainly tie-state buffer, is very much suitable or will be suitable for accessing the input devices. The control signal for this buffer is connected to the result of combining the address signal and IO-RD signal. Address enable signal is generated by combining the address lines and IO-RD control signal. Altogether, it enables that buffer connected with the input device, and whenever in signal is used, the data is read from the input device and being inside the processor. Let's take an example of in instruction used in the IO mapped IO section. Here in 80 instruction is considered. It is basically a 2-byte instruction. So to store this instruction, 2 consecutive memory location is required. Here let us consider 4125 and 4126 are the 2 consecutive address where this instruction is stored. At the first address, the instruction code or opcode DB is stored, which is followed by the port address. Port address of the device is stored in the next memory location, that is 4126. Here we consider that port address is 80. So if we talk about the timing diagram of in instruction, first message cycle is the opcode fetch, where processor read from the address 4025 the opcode DB inside the processor and decoded. Next cycle is the memory read operation. which is read the consecutive byte from the address 4026, and in the third cycle is also a read operation, but it is IO read operation where port address is placed onto the address lines and data available with the input device is read and stored in the accumulator. For example, let us consider with the input device 5E is stored. It will require 3 machine cycles of 10 states, 4 states for the opcode fetch, 3 states for the memory read cycle, and 3 states for the IO read cycle. Let us look at the timing diagram over here. First machine cycle is the opcode fetch cycle, where processor first places the address 4125 onto the address lines. 41 is the higher order address placed onto the A8 to A15 line. 25 is the lower order address placed onto the AD0 to AD7 to uh, make this multiplex line as the address line. AAD signal becomes high at the time of T1. During the T2 and T3 cycle, processor send the read signal. That is the memory related operation, memory read operation. It plays the read signal as low as well as IO M signal as low. IO M signal as low to indicate it is memory read operation. So T2 T3 cycle specially dedicated for read operation from the memory, and during the T4 cycle processor decode the instruction and executes. We must remember that this T4 cycle dedicated for the execution purpose by the processor. Next main cycle begins with placing the next address onto the address lines. 41 is the higher order address. Next address 26 is placed onto the lower order address lines. Here also ALE signal become high only for the first T states, and during the subsequent T state T6 and T7 read operation is performed. The address of the port which is stored in the very next location is read by the processor and bring inside the microprocessor, and in next machine cycle processor places the same address onto the uh, lower order address line. Thus device is enabled or activated, and the signal available with the input device 5E is being inside the processor. Here we do remember that all are read operation. That's why for all 3 cycle read signal is low. It has is do not use the write signal here. No write operation is done. And also remember that for the opcode fetch cycle, memory signal is low, IO signal is low, memory read cycle, IO signal is low. But for the last cycle, which is the IO read cycle, IO signal is high. IO signal is high to indicate that it is IO read operation. Next comes to the in output instruction. Let us discuss about the execution of out instruction by the processor, microprocessor 8085. Like in instruction, it also requires 3 machine cycle for execution with the 10 state. First main cycle known as the instruction fetch cycle, second one is known as the memory read cycle, and third one is known as the IO write cycle, as because here processor will be sending some signal to the output device. Let us discuss clearly with the help of timing diagram. Here we see that first machine cycle, opcode fetch machine cycle or instruction fetch cycle, content of the memory address the memory address is placed onto the address bus, lower order address bus and higher order address bus, which is basically present in the program counter low and program counter high register. 16-bit address is basically available with the program counter that is placed onto the address lines during the T1 cycle. So to make this address data multiplex line as address line only, AEIE signal, address latch enable signal, becomes high. Then during the T2 and T3 cycle, the opcode or hex code present in the memory is placed onto the data lines and bring inside the processor. And during the T4 cycle, as I said, it is the execution time of the processor. During this time, processor execute the instruction and perform its tasks, and understood that it is a out instruction, that means one more subsequent byte from the next memory address also to be read. So what it performs, it places the next memory address which is present in the program counter onto the address lines, and it is done during the first state of the next cycle. And at this time also ALE becomes high. During the T2 and T3 cycle, the content present in that corresponding memory placed onto the data lines and being inside the processor. And when it comes inside the processor, it basically stored in the temporary register W and Z. We must remember that when any content is stored being inside the processor, microprocessor, it has to be stored temporarily. So that is stored in the some temporary register called W and Z. So in the next message cycle, as the purpose or task is not over yet, so in the next message cycle, content of the W and Z register places both onto the lower order address lines as well as higher order address line. Okay. So address is both available in the lower order address line as well as higher order address line. So we can use either of them, but mostly we prefer to use the lower order address lines for enabling the output device. Now, once the address is placed onto the address lines and device is enabled, now the content of the accumulator is placed onto the lines during the next T states, T2 and T3, and sent to the processor. Now, if we look at the control signal status during the operation, we found that first two cycles basically read operation, memory read. So that's why read signal equals to read signal is low during that process, whereas in the third main cycle read signal having no function, that's why it is not enabled. Whereas write signal was throughout high, but during the last machine cycle T2 and T3 time it becomes low to indicate that it is a write operation. Similarly, if we look at the IO ember signal, we observe that throughout the operation M1 cycle and M2 cycle, it is low to indicate that it is a memory related operation, whereas during the last cycle it becomes high to indicate that it is a IO related operation. Other salient feature that we must remember or observe over here, that first of all, content of the program counter at the T1 state of the first message cycle placed onto the address lines, and at that very time it also incremented by 1. Once the content of the program counter placed it incremented by 1, then at the next message cycle also program counter content is placed onto the address lines and it is incremented by 1. So whenever any content of the program counter placed onto the address lines, it automatically incremented by 1 to access the next memory location. And the address of the port read from the memory being inside the processor and stored in the temporary WZ register. Now let us discuss about one hardware configuration uh, to understand how we can connect those host address with the input device or output device. Let us first take the example of input device here. Switches, DIP switches is considered as the input device, and that is connected with the processor through a tri-state buffer. 8-bit tri-state buffer is taken here, and with the help of this tri-state buffer, data or information available with the switches to be sent to the processor. Now, this tri-state buffer having a very important line present with it, apart from the input and output lines, that is the output enable control signal. Until and unless this control signal is becoming low, the no signal from the input side will go to the output side. So to access this information, this signal has to be low. And how it makes low? Now generating with the help of address lines and control signal IOR or IORD. And here one decoder is connected to generate to decode the address available here. Once it is decoded, it produces a low signal here, active low signal at the output of the decoder, and with this combination of IOR generating from IOM and RD, altogether it will produce a active low control signal. In this case, it can be observed that as the OE through a OR gate connected with the Y0 line of the decoder, so to enable the active low signal Y0, A, B, and C input of the 3 to 8 decoder must be 0, 0, 0. Okay. Other three enable line G1 active low, G2 active low, and G active high. It must be G1 must be low, G2 must be low, and G must be high. So A3 low, and to make the G2 signal low, A4, A5, and A6 should also be low, but only A7 must be high. So among these address lines A7 to A0, A7 is high only and remaining 0. So altogether it is 1, 1, and rest of the 7 lines are 0. So if we present it in hexadecimal form, it becomes 8, 0. So to read the status of the input switches, we can write an instruction called in80h. In80h, 80 is the port address of the device according to the hardware connected over here. Similarly, if we want to access the output device, it must be connected through a latch, as I discussed here. So here also one 8-bit latch is connected. 8-bit latch is connected, and its control signal is latch enable. Latch enable signal is connected with the connected through the NOR gate with a decoder, and this time decoder Y1 terminal is connected. So to activate this Y1 as low, it is active low decoder. A0, A1, A2 status must be, A0 should be 1, whereas A1, A2 must be 0, 0. And remaining control signal as previous, G2, G1 active low 0, G2 active low 0, and G active high 1. So 1, 0, 0, 0, 0, 0, 0, 1. 1, zeros, and lastly 1. So it here it is presented. Here it is presented. Oh, sorry. The status of the address lines is presented over here. 1, all zeros, and lastly 1. So ultimately it becomes 8, 1. So to access the output device, here we can write a signal, write an instruction out 80 1 each. So here content of the accumulator will transfer to the output device. Here we can observe that some LEDs are connected with the latch. So to make this LED on or off, a pattern initially has to be loaded in the accumulator. Whatever pattern, which one we want to make on or which one we want to make off, accordingly a pattern to be stored in the accumulator, and that pattern will be sent by using out 81H instruction, and according to that pattern this LED will be on or off. So that's how we can connect output device with the 8085 microprocessor. Keep in mind that when we want to access the output device, address must be properly known. With the wrong address, we cannot access the input or output device. Finally, previous two diagram is combined here. If you want to access both input and output device at the same time, then both can be connected together. Here it is observed that like previous discussion, y1 is connected to the output, y1 decoder output connected to the output devices, y0 controls decoder output, active low decoder output connected to the input devices. If anybody wishes to show the status of the switches onto the display directly, then with the proper address, first of all we can read the input switch status and same to be sent at the output, as because content read content is stored in the accumulator and to be write onto the output device consent also taken from the accumulator. So one can directly send the input status to the output devices by writing only two instructions. First of all, in, if we write like this, in 80H, data will be read from the input device and stored in the accumulator, and at the very beginning, at the very next instruction, if you write the out followed by the address of the output device, that is 81 here, then content of the accumulator present in earlier, from the earlier instruction will transfer to the output device with the address 81. So that's how we can connect or write some program interfacing instruction using 8085 to interface with the input output devices. So that's all for this session. I conclude here. Thank you.